Hello dear students, today's class is specially on graphs of mathematical functions. To solve various mathematical problems, the graphs are very useful. If you know how to draw the graphs, if you know the graphs of various functions, then it is very easy to solve the problem from the graphs. Suppose you want to describe continuity, differentiability, etc., you can describe from the graph itself. So graph is very helpful to solve mathematical problems, especially for joint and IIT. So let us first example that we start from our algebraic graphs. So first expression is a algebraic curves. It's a y equal to x square. It's a polynomial, quadratic polynomial, x square. It's a parabola actually, and the graph is looks like this. X square, it's a even function. Look at that even function, that fx is equal to f of minus x, then the function is said to be even. And even function graphs are always symmetric about y axis. So look at the graph, it's symmetric about y axis. Next graph is y equal to x cube. This is a cubic function, cube, and this is an odd function. Odd function is f of minus x is minus of fx, and this is symmetric about the origin. Look at that, the graph is symmetric about the origin. This is the branch and this is the branch, so it is symmetric about the origin. Next we'll have a simple graph. This is not this is a rational function, 1 by x, x not equal to 0. So as x tends to infinity, y tends to 0. As x goes to x goes to minus infinity, y tends to 0. So this is the graph. In the positive part this is the function, and in the negative part this is the branch. So there are two branches of this graph, 1 by x. Again we have algebraic functions like x to the power 2n, n is equal to 1 2 3. So for 1 2 3 we have drawn the graph for 1 2 3. So x square, x to the power 4 and x to the power 6. Look at that, if 0 less than x, this point is 1, this point is 1. So if x is between 0 to 1, then x square is greater than x to the power 4, x to the power 4 is greater than x to the power 6. So that is why the x square graph is upper, then x to the power 4, the red line, and the blue lines are x to the power 6. But the nature has changed when it is greater than 1, more than 1, then the nature has changed. Look at that, for more than 1, x to the power 6 greater than x to the power 4 and greater than x to the x square. So same thing in the negative side also. So this is the graph for even functions, x to the power 2n. Similarly we'll have graph for odd function, x to the power 2n minus 1. So similar explanations for 0 to 1, we have x greater than x cube, and the red lines are x to the power 5. So for 0 less than x, this is also 1, this point is 1. So 0 less than x less than 1, look at that, x is greater than x cube, greater than x to the power 5. Naturally it's from mathematical point of view. And more than 1, then the nature changes, reverse, x to the power 5 more than x cube more than x. So similarly we have in this side also. So this is your odd function of odd, this is a graph of odd functions. Next we have some trigonometric, simple trigonometric functions. Sine x, already a lot of students know about sine x. Sine x is a wave type curve. So at 0 the value is 0, at pi by 2 this is 1, this is 1, and at pi again 0, 3 pi by 2 minus 1, at 2 pi 0. So let's talk about the domain of this function. Domain is R, this is the domain is whole real line, and this is the range. You look at that, the range is minus 1 to 1, that is it is bounded between minus 1 to 1. This is minus 1 and the upper one is 1. So graph of sine x is bounded between minus 1 and 1. So the range is minus 1 to 1, domain is R, period is 2 pi. After 2 pi the nature will repeat itself, the graphical nature will repeat. That is why the graph is periodicity is 2 pi. And odd function and many one in its actual domain, actually the function is many one. Again we'll see cos x. Cos x this is your cos x. Cos x is a similar wave type curve, and at 0 the value is 1, pi by 2 0, minus pi by 2 0, pi minus 1, and minus pi is also minus 1. So in this way we can draw the cos x. Cos x is also bounded between minus 1 and 1. So the domain of cos x is R, range is minus 1 to 1, period is 2 pi, periodicity of cos x sin x both is 2 pi, but this is cos x is even function because cos of minus x is cos x, and it is many 1 again in its actual domain. Let us draw y equal to tan x. This is the curve of y equal to tan x. So y equal to tan x gives you, this is the y equal to tan x. At 0 it is 0, but at pi by 2 it is undefined. So look at the branch of the curve goes to infinity as x tends to pi by 2. So also the lower part is also goes to infinity. So similar nature in this case also you have the similar branches 3 pi by 2. So it has a discontinuity at minus pi by 2, pi by 2, 3 pi by 2, etc. So for tan x we can say the domain of tan x is r minus 2n plus 1 into pi by 2. That is the discontinuous points, and range is the whole real line because the lower branch goes to minus infinity, upper branch goes to pi by infinity, and the periodicity is pi. Cot x, we have the cot x. Cot x also the domain is cot x also we have 0 at pi by 2 it is 0, and cot x goes to infinity if x goes to 0. So look at the upper branch goes to infinity if x is very close to 0, and also it goes to infinity if the lower branch goes to infinity if it is close to pi. So in this way there is a discontinuity at pi, 2 pi, minus pi, minus 2 pi, etc. So domain of R is n pi, R minus n pi. So if you delete the points n pi, then you get the domain, and range is minus infinity to infinity. Periodicity is again a pi. For tan x and cot x the periodicity is pi, nature is odd, and many 1. Sec x, these are the branches of, there are several branches of sec x. Sec x, this is your sec x, this is a part of the sec x, this is also sec x. So you look at that, a very important feature is that sec x, for sec x all the values will be greater than 1 or less than equal to minus 1. All the values will be greater than equal to 1. Look at that, all the values will be greater than equal to 1. This is 1, this is one line, and this is minus 1 or less than equal to minus 1. That is why the range is minus infinity to minus 1 and 1 to infinity. This is the range, and domain is this r minus 2n plus 1 into pi by 2, because these pi by 2, minus pi by 2, 3 pi by 2, these are the discontinuous point. Let us draw, for example, how to draw the graph of sec x. So this is your x axis and this is your y axis. You know the graph of cos x, this is the graph of cos x, this is the graph of cos x. So you know the graph of cos x is very simple to draw the graph of sec x. Suppose for sec x this will be the branch on the upper part, and on the lower part these are the branches of the sec x. So that is why the graph is looks like this. There are several branches of sec x. So this is how to draw the sec x. So I am not going into the detail of cosec x. Similarly you can explain the cosec x. If you draw the sine curve, it will go through this. If you draw the sine curve like this, if you draw the sin x, then you will get the, similarly if you want to draw like sec x, if you want to draw the sin x, after that you draw several branches of cosec x. So these are the important trigonometric functions. Now inverse trigonometric functions, this is quite difficult to draw, but I will give you a hint for that. Sine inverse, actually inverse function is possible for bijective mapping. If the function is bijective, then only inverse can be drawn. But you see, sine curve of sin x is not bijective, but if you take the branch that is minus 1 to 1 only, then the function is bijective. In that case you can draw the inverse of x. So in that case your domain will be sine inverse x, domain will be -1 to 1 and range will be minus pi by 2 to pi by 2. That is the reverse. So let us have an idea of that. This is sine x, actual sine x, and this is y equal to x line, that is y equal to x will be act as a reflector. So if you take the reflection of sine inverse x, if you draw the graph of sine inverse x by taking reflection on y equal to x, let us illustrate this. Suppose this is your x axis and this is your y axis, and the branch of sine x is, suppose this is your branch of sine x. No, okay, let us try with this. This is your branch of sine x, and suppose this is your y equal to x line. This is your y equal to x line. So now you draw the sine inverse x by taking reflection. So this is your sine inverse x taking reflection on the y equal to x line. So let us draw the y equal to cos inverse x. Cos inverse x is bijective in the range 0 comma pi. So take a branch of that 0 to pi. This is the branch of cos x 0 to pi. Again draw the y equal to x line, that is we want to take the reflection on y equal to x. This is y equal to x line, and now you draw the cos inverse x as a reflection. So this is your cos inverse x. So that is how you have to draw the diagram. So this is the diagram, actual diagram. This is y equal to sine x, the black line. This is y equal to sine inverse x, the red line, and this is y equal to x, where you have to take the reflection. Look at that, it looks like the reflection of the curve on y equal to x. So that is how you have to draw the inverse. And this is also y equal to x, the fair diagram. The black one is the y equal to cos x and the red one is the y equal to cos inverse x. So that is how you have to draw the diagram for inverse function. Similarly, we can draw the tan inverse x. This is y equal to tan x, as already mentioned. This is y equal to x line, the red line, and y equal to tan inverse x, the black line. Look at that, y equal to tan inverse x is increasing function. This is increasing, this is increasing, this is how it is increasing, this is how it is increasing. And what about the tan inverse x, cot inverse x? Cot inverse x, we have, this is your cot x, as already explained. This is cot x, and this black line is the cot inverse x. It's decreasing function. It's please remember, dear students, the cot inverse x is a decreasing function and tan inverse x is a increasing function, and this is y equal to x line. That is how you have to draw the diagram. You can try for sec inverse x and cosec inverse x. Let us have now exponential functions. Exponential functions are also very important, because if you know the diagram, you can solve so many problems on exponential problems. So if the power, that is if a base is greater than 1, then this is the form of exponential function, a to the power x of this type. And if a is 0 less than 1 less than a 0 less than a less than 1, that is a is less than 1, then you have decreasing nature. In this case you have a increasing nature. That is why e to the power x, that is if you take e to the power x, that will be like this, e to the power x. And if you take 2 to the power x, that will be like this, 2 to the power x. That is also an increasing nature. So e to the power x, 2 to the power x, these are all exponential graphs. So what is the domain of this? You see the domain is 0 to infinity, that is the positive half of real axis. Domain is the whole real line, but the range is positive half of the real axis. So you see there is no branch in the lower part, and it is a non-periodic function, and 1 1. Monotonically increasing as we mentioned, and monotonically decreasing when 0 less than a less than 1. So these are 2 to the power x, 4 to the power x, 10 to the power x, and in this side you have a less than 1. So this is how you can draw the exponential graphs. Next we will describe logarithmic functions. As you know, the logarithmic functions are inverse function of the exponential functions. So this is how you have to draw the logarithmic functions. If the base is greater than 1, if the base is greater than 1, look at that, the base is greater than 1, then log x is increasing. this is how increasing, then log x, but if the base is less than 1, then log x is decreasing, so you have several diagrams, log 2, log 3, log 5. So this is how you have to draw the logarithmic functions. Is very very important, logarithm and exponential. Next we'll talk about a special type of functions which is known as signum function. Signum function is nothing but mod x by x, and you know that mod x is x when x is greater than 0, and mod x is minus x when x is less than 0. That is, if you want to draw the mod x, simply you draw the axis, and this is your x and this is your y equal to x, this branch is your y equal to x and this branch is your y equal to minus x. So this is the diagram of mod x. So mod x is x when x is positive, so in that case you have y equal to 1 as a branch, x not equal to 0, so there, and y equal to minus 1 when x is less than 0. So in the negative part you have y equal to minus 1, in the positive part you have y equal to 1. So x greater than 0, y equal to 1, so there is a jump discontinuity here. So this is how you define signum function. Is very very important, signum functions. Next, as a very important functions for all the mathematics people, that greatest integer function, that is mod x is defined greatest integer less than equal to x, greatest integer less than equal to x. How will you define greatest integer less than equal to x? Suppose the function, the x is 0 to 1, then the value will be 0. 0 less than x less than 1. If the value is 0, if the value of x is 0 less than x less than 1, then it will take 0, because less than 1 the integer nearest greatest integer value is 0, so it will, the graph branch of the graph will be this. And if it is 1 to 2, then it is discontinuous on the right end point. So look at that, there is a gap at the right end point. So if it is 1 to 2, the value of the graph will be 1. If it is 2 to 3, the value of the graph will be 2, because it has a discontinuous at the right end point, and 2 is the greatest integer less than equal to x. Similarly on the negative branch, if it is minus 1 to 0, it will be minus 1, and it will be minus 2 to minus 1, it will be minus 2, and so on. So the greatest integer functions are very very important. We will see in the next video, I will post that so many greatest integer functions, applications of greatest integer functions, sine box x or box sine x, cos x, box cos x, so on. So domain of R is R, domain of this function is R, and range is Z integer. So you have some properties on that. These are the important properties. Box x lies between x minus 1 and less than equal to x. Let's move on to fractional part of x. Fractional part of x is given by x minus box x. Yeah, this is, that means if you subtract the integral part from x, then you will have the decimal part or the fractional part. And look at that, fractional part always lies between 0 and 1. Yes, suppose 2.9, what is the greatest integer? 2. So 2.9 minus 2, that will be 2. 0.9. So 0.9 is a function, it's a value lies between 0 and 1. That is why the greatest integer fractional part lies between 0 and 1. So look at that branch, 0 to 1, 1 to 2. So always lies between 0 and 1. Greatest fractional part always lies between 0 and 1, so on. So this is the diagram of fractional part of x. This is also very useful, and you have so many problems in domain, range, and continuity, differentiability involving greatest integer function and fractional part of s. That is why domain is of this function, fractional part is R, but the range is 0 to 1. You look at the graph that the value is bounded between 0 and 1. It is discontinuous at 1. So there is an open interval, and periodicity is 1, because the nature of the curve repeats after 1. So at equal interval of 1. So 1 is the periodicity. So fractional part has a periodicity 1. So there are so many properties. So I hope this video, today's video will be helpful to solve you so many problems in calculus, in domain, in range, in so many branches of mathematics. So dear students, go through this video and subscribe my channel, and go just look at the next video. I will post it very soon. Thank you.